So we're learning about the basics of hypothesis tests, which are also called statistical tests. And so in class the other day we talked about the difference between the null and the alternative hypothesis, and that there's typically a claim that's being made, and we're trying to see if we have evidence in favor of that claim or against that claim. We also talked about the different types of errors that can be made, the type 1 and the type 2 error. So a hypothesis test, also known as a statistical test, is something where, all right, after we state the null and the alternative hypothesis and we specify a particular level of significance, and we said those most reasonable levels of significance or most common are 0.10, 0.05, and 0.01, then what we want to try to do is compare the statistic that we get from our sample to the claim that is made about the population value. So we want to make sure we're clear on the different notations that we use. So because we're going to compare our sample value to a population value, we want to make sure we're very clear on the difference between the notations that are used for sample values, also known as statistics, and population values, also known as parameters. So if we're testing a claim made about a population mean, then we know that the symbol we use for population mean is mu, whereas the symbol we use for sample mean is x bar. So our population parameter would be mu, our sample statistic would be x bar. And we know that we can use, given what we learned about confidence intervals for means, we can use either z or t for these tests. Z is when you know sigma. We know the population standard deviation, whereas t is when we do not know the population standard deviation. So with means, we can use either z or t, depending upon what we know. Another population parameter is the population proportion. The notation we use is p for the population proportion, and for the sample proportion it is p hat. And like with confidence intervals, we learned that we could use the normal curve or z distribution to construct a confidence interval to try to estimate a population proportion. So we'll also be using z to carry out a hypothesis test for a population proportion. Now, in the process of conducting a hypothesis test, we're going to get to a part where we will actually determine how likely it is for us to get sample results like we got, or even more different from what is claimed. And that probability is known as the p-value. So say, for instance, there's a claim made about a population proportion. Say they claim that the proportion of drivers who run red lights is 0.45. And we believe it's actually more than 0.45. So we go and we take a random sample of drivers from the population, and we find that in our random sample, our p hat, our sample proportion that run red lights, was 0.70. Well, since our claim was that, or our belief is, that more than 45% run red lights, and we got a sample proportion that run red lights equal to 0.70, then the area in this tail is what is called the p-value. It's the probability that we would get sample results this extreme or more extreme if this is really true. And so when that p-value is really small, then that means that the likelihood of us getting sample results this far out or further, if this is really true, that likelihood is very small, and it makes us think that that p is 0.45 is a false statement. And so we'll be constructing or calculating p-values when we actually go about carrying out hypothesis tests. Now, a test can be one of three types. It can be left-tailed, where in the ha, we say that mu or p is less than a number. It can be right-tailed, where in the ha, we say that mu or p is greater than a number. Or it can be two-tailed, where in the ha, we say that mu or p is not equal to a number. And so, depending upon the direction of the alternative, less than, greater than, or not equal to, our hypothesis test can be left-tailed, right-tailed, or two-tailed. When it's left-tailed, we take our sample results. In this example, I have mu that I'm running a test against, or a test in favor of. And we take our sample results when it's less than, and we're finding the probability of that left tail. When it's right-tailed, again, our alternative will say that mu is greater than a number. And so we'll be finding the area in this tail above our test statistic. And once again, when it's two-tailed, that's when we're not sure if it's going to be, and this didn't come through, so let me rewrite it. Sure if it's going to be less than or greater, we just believe it's going to be different. So our alternative will have a not equal to sign in it, and that means we don't know if it might be in this tail or in this tail. And so the p-value is the area of one of those tails doubled. And we'll learn more about that when we get to lesson 7-2. So let's practice identifying whether or not we have a left-tailed, right-tailed, or two-tailed test. Let's say that a school publicizes that the proportion of its students who are involved in at least one extracurricular activity is 61%. Well, we talked in class the other day about the fact that, okay, then in the null, we would say that p is equal to 0.61. Our alternative, they did not say that they thought it was more or that they thought it was less, and therefore our alternative would just be that p is not equal to 0.61. So you notice that in our alternative we have a not equal to, and a not equal to is always a two-tailed test. We weren't sure it was going to be less or if it was going to be more. We just think it's going to be different, and that's always a two-tailed test. Or here's another. A car dealership announces that the mean time, so this is about mu, for an oil change is less than 15 minutes. So we know that the inequality always belongs in the alternative hypothesis. So in our alternative, we would say that mu is less than 15. Our null would therefore say that mu is greater than or equal to 15, which we have again identified is the complement. So we look at our alternative hypothesis in order to help us determine if it's a left-tailed, right-tailed, or two-tailed test. It's pointing to the left, and therefore it is a left-tailed test. Here's another. A company advertises that the mean life, again it's about means, so our null and alternative will be claims about mu. The mean life of its furnaces is more than 18 years. More than is an inequality. The inequality always goes in the alternative, so the claim is in the alternative here. The complement of more than 18 is less than or equal to 18. So that's what would belong in the null hypothesis. To determine whether this is a left-tailed, right-tailed, or two-tailed test, we look at the inequality used in the alternative. It's pointing to the right, and therefore it is a right-tailed test. So when we learn to conduct a hypothesis test in its full form, after we compute, or after we determine if it is a right-tailed, left-tailed, or two-tailed test, we'll be computing that p-value, that probability of being that far out or further if the null hypothesis is really true, and we'll use that p-value to make a decision, okay? Now my formatting didn't come through okay here, so let me identify here that if p is less than or equal to the level of significance provided or given, we learn that alpha is level of significance. If our p is less, then we'll reject the null, or equal to. If p is more than alpha, then we will fail to reject the null. So when we reject the null, we say that there is enough evidence against the claim, or evidence to reject. When we fail to reject, we say that there is not enough evidence to reject. Now, when we reject the null, that means we have evidence to reject that. So therefore, there is evidence to support the alternative, okay? So if we reject the null, then we have evidence to support the alternative. Whereas when we fail to reject the null, then there is not evidence to support the alternative. So there's evidence for only one hypothesis. That means there's not evidence for the other. So if we have evidence for the ho, we don't have evidence for the ha. If we don't have evidence for the ho, then we do have evidence for the ha. So let's say that the ho says that a school publicizes that the proportion of its students who are involved in at least one extracurricular activity is 0.61. And we conduct a hypothesis test. How should we interpret our decision if we reject the ho? Well, if we reject the ho, then we have evidence in favor or in support of the ha. Okay? So if we reject the ho, then that means we believe we have evidence to support the ha. So in this case, we identified that the ha would say that the proportion is not equal to 0.61. And so that's exactly what we would say. If we reject the ho, we would conclude there's evidence to reject the school's claim that the proportion of students who are involved in at least one extracurricular activity is 0.61. So we're rejecting the ho, but now we have evidence in favor of the ha, which of course is we have evidence to say that the proportion is different from 0.61. On the other hand, if we fail to reject the ho, that means we don't have evidence to say it isn't true. So therefore, we believe we have evidence to say that it is true. So we could say there is not enough evidence to reject the school's claim, because remember the claim in this case was that the proportion of students involved in at least one extracurricular activity was 61% or 0.61. So if we fail to reject the ho, that means we believe that that claim is true, that the proportion of students who are involved in at least one extracurricular activity is 61%. We believe that to be true. So back to the car dealership example. If a car dealership announces that the mean time for an oil change is less than 15 minutes, then we said that less than 15 minutes belongs in the ha. The complement of that in this case would be greater than or equal to 15 minutes, and the statement of equality always belongs in the ho. So if we were to reject the ho, then we would be saying that we have evidence to say that this is not true. So we have evidence to say that the mean time for an oil change is not greater than or equal to 15, but rather less than 15. If we fail to reject the ho, that means we don't have evidence to say that the mean time for an oil change is greater than 15 minutes. Greater than or equal, excuse me. Let me say that again because I might have said it backwards. If we fail to reject the ho, that means we don't have evidence to say that the ha is true. So we don't have evidence to say that the mean time for an oil change is less than 15 minutes. All right, so to finalize this introduction to hypothesis tests, I want to go through the process that we will be following when we actually conduct one of these tests in its formal form. So first, we're going to state a null and alternative hypothesis. Second, a level of significance will be established for us, or we will establish one. Third, we'll determine a standardized test statistic or a standardized sampling distribution, whether it be Z or T. Fourth, we'll calculate a test statistic. We'll find the p-value. And sixth, we'll make a decision. Are we going to reject the ho and say we have evidence in favor of the alternative? Or are we going to fail to reject the ho and say that we believe that it is actually true? And then seventh, we'll write a statement that interprets the decision that we made in the context of the original claim. So my next video is going to be with regards to actually carrying out this 7-step process with a claim that's made about a population mean and or a population proportion. Our next video, though, will be about population means.